Good afternoon, everyone. Today is the second class of this mini course about the maximum monotone operator and the splitting method. Before we go to the class today, let's recall about the some things we have discussed before. So last time we discussed several problems which can be recognized, which can be regarded as a maximal inclusion problem. First, it's the unconstrained problem. We want to minimize a function such that x belongs to Rn, and the optimal validity condition is we want to find the 0 belongs to the subdifferential of a point x star. Okay, so we can also have a constraint problem. We want to minimize fx such that x belongs to a convex set C, and it is the optimality condition is we want to find 0 belongs to, we want to find some point such that x0 belongs to the subdifferential of x star plus the normal cone of normal cone respect to C of x star. Exclusive these two problems, we can also have the variational inequality problem, which is we want to find a point x star belongs to the set C such that fx star, the inner product of fx star, x minus x star is greater than 0 for any x belongs to a closed convex set C. Okay, and the optimality condition for this variational inequality problem is that we want to find some point such that 0 belongs to the fx star plus the normal cone of C of x star. Okay, and another problem which can also regarded as the maximum monotone inclusion problem is that the convex feasibility problem, which is we want to find a point x star belongs to the intersection of two convex and closed sides. Okay, so it is the optimal condition is the x star belongs to the the 0 belongs to the normal cone of A x star plus the normal cone of B x star. Okay, if we have the point x star such that 0 belongs to the normal cone of A plus normal cone of B, then it is equivalent to solve this problem. So all of these problems could be regarded as this one. We want to find a point ax such that 0 belongs to the ax, and A has some properties here. It could be maximal monotone. Okay, so we have discussed this kind of problems. Corresponding, we have discussed some property of the functions among these problems and operator among these problems. First, we have studied a function f, which is called a CCP function. Okay, CCP means closed, convex, and proper. Okay, and we can use another definition, which is called the epigraph of the function f, to discuss the corresponding properties. For example, if the epigraph of a function is closed, convex, and does not contain any vertical lines, it is, we can say the function f could be CCP function. We have an example here. For example, the graph of the negative log function. The epigraph of the function is like this. So it is closed, convex, and without any vertical line containing it. Okay, so after the CCP function, we have discussed another property which is stronger than the convex, which is called strongly convex. Strongly convex. And also we have discussed another property is called L-smooth. L-smooth. The strongly convex means a function which has a lower bound slope. The graph has a lower bound slope, slope, and the L-smooth function means the slope of the graph of the function could be at most of some constant, okay? And these two properties are dual properties by the function f and the conjugate function, okay? If f is strongly convex, and then we see that it is equivalent to say the conjugate function f is L-smooth. Okay, so this is the first property we talked about the functions. And we also talk about the properties of some operators, okay? Because here we involved operator A and we involved operator F in the variational equality and the maximum monotone inclusion problems. So we have the most basic one, okay? The monotone. Monotone operator, which if operator T is monotone, it means the T of x minus T of y and x minus y, the inner product is greater than 0 for any x and y belongs to the, we assume that the domain of the operator T is a whole space. So if this inequality holds, it means the operator T is monotone. And furthermore, we have maximal monotone. Maximal monotone. What does it mean? If T is maximal monotone, we cannot find another monotone operator S such that the graph of T can be contained of a graph of S. Okay, so properly. So you cannot find another monotone operator such that the graph of T can be contained in the graph of S. So if this doesn't exist, we say T is maximal monotone. We have some examples of maximal monotone operators. First, the normal cone with respect to C. The normal cone vector of a convex site which is a maximal monotone operator. Here, we should also have some examples of the CCP function. The very interesting example is that the indicator function of some set C, okay? This function is CCP. Okay, let's go back to the examples of maximal monotone operator. First example is the normal cone, okay? And the second example, we have the projection. The projection of some point onto a set convex and closed set C. Okay, so we can have another example is continuous operator. If T is continuous with the domain from Rn to Rn, then we say T is also the maximal monotone operators. Except these examples, we can also have some properties, some operations which can preserve the maximal monotone. I will put it here. First, if T is maximal monotone, then the T inverse is also maximal monotone. Okay, this is very important. And another one is the summation of two operators. We need to pay attention here. If T and S are both monotone, okay, monotone, then the summation is also monotone. This conclusion is okay. But if T is maximal monotone and S is also maximal monotone, then the summation is maximum monotone or no. It is not determined. It requires some assumptions. It requires, for example, if the domain of T in the product with the interior of the domain of S is not empty, then we can say that the summation of two maximum monotone operators are still maximum monotone. Okay, and after we have discussed the monotone and the maximum monotone, we have some further properties about the monotonicity. One is called strongly monotone, and another is called coercive. Okay, so the definition of the strongly monotone is like this. The left side is the left side is the same as the equality for the monotone operator. Okay, so it's the same tx minus tyx minus y. But here is not only greater than 0. Here is greater than some constant mu times x minus y square. Okay, and coercive is similar. Here is tx minus ty, and x minus y is greater than some constant beta, and here is x minus y square. Why should we study the further stronger property of monotonicity, like here, the strongly monotone and the coercive? Because in some problems, the operators could have a better property, even stronger than the monotone. So we can have some better convergence result about this kind of problems. And it's like strongly convexity and L smoothness. They are dual properties. Here, these two properties are also dual properties by the operator T and T inverse. Okay? If the operator T is strongly monotone with the parameter mu, then we see that the T inverse is coercive with the parameter 1 over mu. So these two properties are also dual properties with each other, corresponding to the operator T and the T inverse. Okay, so this is the property of functions and operators which among the problems. And next, we have discussed this a little bit in last class, just to begin a little bit, which is the algorithms. Okay, the first algorithm we talked here is the most abstract. It's the fixed point iteration. Fixed point iteration. The scheme is xk plus 1 equals to some operator t, and the input is xk. Okay. So when we analyze the convergence of the fixed point iteration, we need to have some properties of the operator here. The most famous and the simplest one is the contraction. Okay, contraction. If the operator T satisfies T of x minus T of y is less than some constant q, x minus times the norm of x minus y. If q belongs to 0 and 1, then we say this operator T is a contraction. And according to the Banach fixed point method, we know that the fixed point iteration converges. The sequence converges to the unique point, and in the Hilbert space, it converges strongly. And but usually, this kind of contractions is is a very strong assumptions. In some cases, we cannot require operator is contraction. So we have another definition, assumption about the operator which is called non-expansive, which means if the operator tx minus ty, the norm is less than the norm of xy, then we see that the operator t is non-expansive, okay? But unfortunately, if we only assume that the operator t is non-expansive, we cannot get the convergence of the fixed point iteration. We have a counterexample here. If the operator t equals to the 0, minus 1, 1, 0, it's the 90-degree rotation, okay? And if your initial point, x0, is not the original point in the R2, then your iteration, your fixed point iteration with this operator will never converge, okay? Will never converge. So, according to this example, we can see that non-expansiveness is not enough to guarantee the convergence. So we need something stronger. Here we call it's called averaged. What is the averaged operator looks like? If t is averaged, we say that it could be written as a convex combination of identity operator and some operator s, and here s is what we call is non-expansiveness, non-expansive operator. Non-expansive operator, okay? So, and the parameter theta belongs to 0 and 1. It could be not equals to 0 or 1. If it is equal 0, it is non-expansive, okay? So, if the operator is satisfied the assumption of average, then the corresponding fixed point iteration converge. Okay, this is what we are going to talk about today. Okay, let's go back to our slide. And so we begin from here. We have iteration scheme. We have iteration scheme. Okay, thank you. So how do we use the strategy of using the fixed point method to solve our problems is like this. We need to find the correct operator which can guarantee the fixed point as the solutions of the original problem which we are interested in, and then we analyze the convergence of the fixed point iteration. Okay, let's go to the example. We have discussed the example before. We want to minimize a unconstrained problem, minimize function f such that x belongs to the whole space, and the optimality condition is 0 belongs to the gradient equals 0. Actually, here we assume that it's differential, okay? So it's equivalent to this, and we can see that the stationary point x, if the gradient x equals 0, okay, then we call it a stationary point of the unconstrained problems is the fixed point of this operator. Okay, we get this from the analysis here. Then it is natural to consider, instead of solving these problems, can we use a fixed point iteration with respect to this operator to find the fixed point of this operator and then corresponding the stationary point of their corresponding problem. So we consider the iteration like this, okay? Xk plus 1 equals to identity minus alpha, the gradient of the grade of f at point xk. We define it as the operator t. Of course, if you do not assume f is differentiable, f is just convex function, we can use the subgradient here, okay? Subgradient here. So 2 ways to analyze the convergence we have mentioned before. First, we analyze the function f decrease sufficiently. If we check the textbook about the method using imageal search or some other kind of line search strategy, it will analyze in this way. And also we can analyze if x gets strictly closer to the solution. Okay, so the most if we have this inequality, if Q belongs to this is what we have analysis called a contraction. Okay, if it is contraction, it will converge by according to the Banach fixed point theory. Okay. Let's still go back to the gradient descent method. Okay, and here we assume that f is mu strongly convex and the Lipschitz constant, Lipschitz continuous. We see that this assumption is very strong. Okay, it's a very strong assumption. We will talk about this later. And let's analyze here. Okay, we assume we calculate the norm of tx minus ty squared. It equals to this one just by the definition of the operator t. And we expand this, we get this equality. And we also expand this one, we get this equality. 2 terms and with this term. Here, from this inequality, we use the assumptions of strongly convex and the Lipschitz constant, Lipschitz continuous. Okay, for this term, since f is L Lipschitz continuous, then we see that the L smooth. Okay, then the gradient is Lipschitz continuous. Okay, so we use the gradient is Lipschitz continuous for the second term, and for the third term we use the strongly convexity. So we can get this less than or equal to, because you have a minus here. Okay, the minus plus the strongly convexity, you get this inequality. Okay, we define this 1 plus lambda square L square minus 2 lambda mu equals to 1 minus tau. Okay, so if we can assume that this constant 1 minus tau is less than 1, then we can get this operator is contraction. Okay, and it is possible if we assume the alpha. Okay, alpha here. Alpha, what is alpha? Let's go back to this slide. No. What is alpha? Okay, alpha here. Alpha is the step size of this gradient descent method. But before, we have no assumption of the step size. But here, we will have the interval of the step size to guarantee or to make the operator t to be a contraction. Okay, so since it is a contraction, we have the convergence. Xk will converge to x star with a rate of 1 minus tau. Okay, let's analyze a little bit more. Here we need the assumption about strongly convex and L smooth. Okay, then about the function f. Then we get the operator t. The operator t here is, we need to pay attention. The operator t here is the identity minus alpha, the gradient of f. This is operator t here in this fixed point iteration. These 2 assumptions, which can give you some examples, like a quadratic function, but the derivative of the quadratic functions must have a upper bound and a lower bound, so it cannot cover many examples in the real world. Okay, so we need some weaker assumptions to guarantee the conclusion, instead of using the concept of contraction. It's non-expansiveness, okay, which I have mentioned on the blackboard before. If it is satisfies this inequality, then we call it non-expansive. We have some properties of about the non-expansive. Okay, let's say if T and S are expansive, the component is non-expansive. T and S are one of them is contraction, then the composition is contraction. If one of them and the convex combination of T and S are still non-expansive, okay? But we need to here theta could be 0 and 1. And if one of them is contraction, the convex combination is also contraction. But you need to be attention, theta could not be 0. If theta is 0, then it is just the operator S. Okay, so here is an example I mentioned before. I mentioned before that the non-expansive operators cannot guarantee the convergence, okay? But we will not see too much here. And then we need the average operator, which is stronger than non-expansiveness, but weaker than the contraction. It's just a combination of the identity and non-expansive operator, okay? And if the theta equals to 1 or 2, we call it firmly non-expansive. This kind of definition, firmly non-expansiveness, has been used in a lot of papers or textbooks. It's so we mentioned it here. And we have some assumption. We have some property here. Okay, if T and S, both of them are averaged, then composition are still averaged. We will use assumptions these properties to analyze something in the convex feasibility problems later. Okay. So this averagedness is a base for the convergence of many splitting methods, also the base of the proximate point method. Okay, let's go to the examples in convex feasibility problems. Let's see the difference of the averaged operator and the non-expansive operator. Okay, we want to find a point in the intersection of A and B. Here, A, B are both closed and convex. Among the algorithms for solving this kind of problems, two kind of operators are widely used. First is projection, okay, the orthogonal projection, and the second is reflection. The projection is defined by the minimum of the distance from the point X to the set A, and the reflection is defined by 2 times the PA minus identity. We need to be attention here. The cost of the projection and the reflection are almost the same. If you already have the projection here, you can get the reflection automatically. So the cost of the calculation of these two operators are the same. Okay. And we have properties about these two operators. First, the projections is averaged operator, okay, and the reflection is non-expansive. Because of this difference, when the algorithms use these two different operators, it will give you different performance. First, we consider okay, before we analyze the algorithms here, we need to see the fact that if the x is the fixed point of the component of PA and PB, then x belongs to the intersection. If x is the fixed point of this operator, which is component of reflection A and reflection B, it also belongs to the intersection. So these two facts is the base of the algorithms, the following two algorithms, which we use the fixed point iteration to solve feasibility problems. First, let's go to analysis these algorithms. This is called the alternating projection method, which we from point xk, we first project to point A, and then we project to point B. And by the property we discussed before, we know the composition of two averaged operator is still an averaged operator. So obviously, these algorithms or the first point iteration, the first one, this fixed point iteration will converge, okay, because it's an average operator. But the second is not, okay, because the composition of two non-expensive operators are still non-expensive. We can see an example here on the blackboard. If we assume the A and B are these two lines, okay, and we have an initial point here, x0. If we use the fixed point, the second one, the composition of reflection, okay? So what is the performance? You first reflect to A. This is projection, okay? This is PAX0. Okay, this is a reflection. This is what we call RAX0, okay? So after you get the first reflection, you do the reflection to B, okay? Projection, reflection. So this point is RB, RAX0, okay? So after we do one step iteration, 2 times the composition of reflection, we get the point here. Okay, we can call this point x1. Okay, so this is the first iteration. So you do another one. Where is the point? So first you do reflection to A, and then you do reflection to B. Okay, you go back to the point. So this example shows if we use the composition of reflections, which is a non-expensive operator, then you cannot get the convergence. But if we can just make a little bit modification about these algorithms, then we can get the convergence. And also maybe we can get a better, faster algorithm than these classic algorithms, the composition of the projection. For the operator A, we do a convex combination with operator I, okay, identity. For operator B, we also do a convex combination with I. Of course, here, the theta cannot be 0 and 1. Should be greater than 0 and less than 1. With such kind of convex combination, we know these two operators are both non-averaged. And the combination of average operator is still average. So in these cases, the convergence will, the sequence will convergence. Why people, we may have a doubt here. Since we already have the projections, which can guarantee the convergence, okay, because in the first one, the composition of the projection, we can get the convergence. Why still we use the reflection? Because in some cases, when the interior of the A and B are non-empty, the reflection operator RA could accelerate the convergence. That's why in some papers we use this we do not use the reflection operator directly, but we use somehow the combination. Okay, so this is the a point of view from the operators to analysis some algorithms for convex feasibility algorithms in convex feasibility problems. Okay, so let's go to the main algorithms in the first slide. Okay, we talked a lot about the averaged operator. Okay, we talk. But why does the fixed point iteration converge with averaged operator? This theorem explains the reason. Okay, So the assumption is theta averaged and the fixed point of t is non-empty. Then we can have the convergence. Pay attention, the convergence here is in the Euclidean space, not in the Hilbert space. So we do not have the difference between weak convergence and strongly convergence, okay? So first, we can have the content is distance from xk to the fixed point, and the distance between 2 points, and the distance between the xk and the norm of xk minus the solution. All of them are decreasing, okay? Are monotonically decreasing. And furthermore, finally, we can have the distance between the xk to the fixed point set is 0. This explains this is the convergence, okay? And we can have the rate with the theta over k plus 1 times 1 over 1 minus theta, okay? So actually, if you check some papers, the theorems, the convergence analysis may be different, but they may be similar, okay? Many of them are based on the framework we have discussed here today. So here is another example to say, if we have an averaged operator, okay, if you assume that t is minus 1, then you cannot get this convergence here, okay? You see the point is get closer and closer and closer and closer to this, to the fixed point of t. The fixed point of t is here, this vertical line, okay? Because the t is the 3 over 4 averaged, okay? Because it could be, this t could be average of the identity and the convex combination of identity and minus 1, the operator here. Okay, so before we go to the proof of the theorem 1, we need to mention a result, okay? If we which can be used in the analysis of theorem 1. If we have two negative sequences vk and sk, and satisfy this inequality, then we have two conclusions. First is vk is monotonically decreasing, okay? So this is, we can get the first one automatically, okay, very intuitively, and then s approaches 0. Why? We sum both sides, okay, from 0. We sum the inequalities on both sides from 0 to k. Then we have this inequality. The sum of s from 0 to k is less than v0 minus vk1. Since they are non-negative, so this is less than or equal to v0, okay? So it means we take k to the infinity. So this means the sequence S is summable, okay? Since it is summable as k approaches 0. We use these properties in the following convergence. Okay, to prove the theorem 1, let's recall what is theorem 1. It says the fixed point iteration with averaged operator convergence, okay? So first we have identity of this. If we expand a convex combination of x and y, we get this identity, okay? 3 terms, 3 square terms, okay? And the t, since t is average, it can be written as a convex combination of identity with a non-expensive operator s. Then we have this fixed point iteration, okay? The fixed point iteration can write as 1 minus theta xk plus theta x ssk. Okay, so we analyze the norm square of xk plus 1 minus x star. by the identity here, okay, identity here, we can expand this term, this square, to the sum of three terms, three square terms, okay? Xk minus x star, s xk minus x star, and s xk minus xk. And next, we will use the property of s. Okay, the first term didn't change, it's the same. And the last term didn't change, it's still here. What did we use here? We used the property of the non-expansive of the operator s, okay? Here, we know that since x star is a fixed point, so x star equals to s x star, okay? First, it can be written as s x star, then we use the property of the operator s. Then we get this one. And then we reorganize these three terms together, we get this one, okay? We get this one. Okay. This inequality one, this inequality 1 is the most important inequality in analysis here. So, since the theta is greater than 0 and less than 1, so this terms is somehow negative, and then we can get xk plus 1 minus x star is less than xk minus x star, which means the xk, the distance from xk to the fixed point x star will not increase, okay? Maybe decrease, but at least not increase. We minimize on both sides of this inequality, okay? We get with respect to x, x, because x star is any fixed point, could be arbitrary fixed point of the operator f. So we get this distance, okay? We get the distance from xk to the fixed point is less than the distance of the xk to the fixed point. And such kind of properties is called feature monotonicity, okay? Feature monotone. But we will not discuss this definition here too much. Okay, to analysis the convergence in fixed point iteration, we usually analyze what we call fixed point residual here, which is txx, or we can write it as xk plus 1 minus xk. We will see later why we can analyze this term to say whether the sequence converges or not. Okay, so since t is non-expansive, we can get this automatically, okay? And from the inequality 1, what is inequality 1? Let's recall it again. It's xk plus 1 minus x star square less than xk minus x star square and minus and have a negative term here, okay? Remember, it is a negative term. Okay, we sum this inequality from k equals to 0 to k equals to from j to equals 0 to j equals to k. Okay, we have so we have this inequality. Okay. And we sum it from j equals to 0 to k. And we rewrite it, reorganize it, and we put these terms on the left side and this term right side, okay? And divided by this constant. And then we get this. And be careful. We have analysis among all these terms here, okay? Among all these terms here. The distance, the xk plus 1 minus s is decreasing, let's say here, okay? the xk plus 1 minus xk is less than the xk minus 1. It's monotonically decreasing. This is because of the operator t is non-expansive, okay? It's non-expansive. So among all these terms here, we have k plus 1 terms. The smallest one is the last term, okay? So it could be less than the last term, xk plus 1 minus xk. And the k plus 1 is the number of the terms here, okay? And we have this is less than this sum of term, okay? And less than this term, because this term is negative, we can eliminate, is negative, we can eliminate. So we have this inequality, okay? And from this inequality, from the left side, the most left side and most right side, we get this, we conclude this inequality, okay? And from this inequality, we take the minimize, okay? Since we minimize on both sides of the inequality, okay? Since x star is the any point in the fixed point side, so we get this is the distance square of the distance from x0 to the fixed point side, t. And let's analyze this here. On the right side, this term actually is a constant, okay, because the initial point is fixed, and the fixed point is also some fixed side, okay? And as the k increasing, the right side is decreased, and when k approaches infinity, the right side will approach 0, okay, approaches 0. So we have that. So sorry. So from this inequality, we can see the conclusion. We can see that the distance, we already get this inequality, okay? We already got this inequality. And next, we want to show that the whole sequence xk approaches x star, and x star is exact some fixed point, okay? We analyze this in this three steps, okay? First, we can conclude that xk has a accumulation point, and then we assume that the accumulation point is a solution, and then we see that the whole sequence will converge to this accumulation point. This is the strategy here. Okay, so first we consider this x tilde star is any point in the fixed iteration, okay, in the fixed point side. This is not the accumulation point, okay? And the inequality, the first inequality told us that the x0, the whole sequence lies in the compact side, okay? The compact side is defined by this. Or we can say that the whole sequence, the sequence is bounded, okay? Then we can have a accumulation point x star, okay? Be careful, x star is the accumulation point, and the x tilde star is the is the solution, or is a fixed point side, okay? Next, let's see that's analysis whether this accumulation point belongs to the fixed point set. Okay, so since the since xk is the x star is a accumulation point, we can have this xk. Let's go to the blackboard, okay? First, we already have txk minus xk. This approaches 0, okay? Since that x star is accumulation point, so we can have tx star is minus x star is equal 0. Okay, and since the t minus identity is continuous, then we can include by this identity that x star belongs to the fixed point side, okay? So first we have a accumulation point because of the sequence is bounded. And the second, we prove this accumulation point is a fixed point. And then we want to show the whole sequence xk converges to this x star, okay? So we just use the inequality 1 first, okay? Because we know that from the inequality, first inequality, we know xk minus x star is monotone decreasing. But from the, let's go back here. Okay, from this inequality, we see that the xk plus 1 minus x star, this term is monotonically decreasing because this term is negative. And let's go back. Okay, here. And we know that there is a subsequence, okay, because x star is accumulation point of the sequence xk. And we can assume that there is a subsequence xkj such that this xkj approaches x star, and then we apply the first inequality to this subsequence. Then we can not only get that this monotone decrease, but also monotone decrease, furthermore, monotonically decrease to 0, okay? So we can see that the whole sequence converges to x star. So this is the analysis for the theorem 1. Okay, theorem 1. Let's just summarize a little bit. First, we have this inequality, okay? First, we have this very important inequality. The inequality comes from the definition of the operator T and the non-expansive of operator S. Okay, we use the property of non-expansive here to the second term in the first inequality. And from this inequality, we get first this decrease, okay, xk minus x star decrease, and we also have from the first inequality, we also get from the first inequality, we make the summation on both sides, okay, and then we get this one, and until we get this one, okay. From this one, we know that xk plus 1 minus x approaches 0 as k approaches infinity, okay. So after that, we just analysis. How can we conclude the whole sequence converges x star, which x star is a fixed point? We first by the boundedness of the sequence, we have accumulation point, and then we see the accumulation point is a fixed point, and then we use the inequality again to see that the whole sequence converges to x star. Okay, so according to the analysis, we see that these terms, the distance between xk plus 1 minus xk, it will approach 0 if the whole sequence approaches, okay? So we can use this fixed point residue to measure whether the sequence converge and how long does the sequence the distance between the sequence and the solution side, okay? So of course, you can use some other kind of stopping criteria, but this could be a general stopping criteria. Okay, so let's consider some examples with this theorem we analyzed before, or we just analyzed. We go back to the gradient descent method. We want to minimize this function. Okay, we assume f is CCP and differentiable. Just to recall a little bit, in the previous slide, we analysis not by the averaged operator. We analysis the convergence by the contraction, by the contraction and Banach fixed point theory. At there, we assume that f is strongly convex and L smooth, which is a very strong assumption. But here, we just need to assume that f is CCP and differentiable, okay? Then we see that these are equivalent, okay? If x is the minimizer, then x is the fixed point of this operator, okay? So the fixed point iteration is like this. It's the same as before. And okay, since let's analysis the property of this operator. Sorry, let's analysis of the operator here with the new assumptions, weaker assumptions. Okay. First, we can see that the identity minus alpha grade f can be write a convex combination of the identity of I minus 2 over L, the grade f, okay? If we assume f is a smooth, okay, if we assume f is a smooth, then by coercive, because for the gradient, for the subgradient as we discussed in the last class, for the subgradient or gradient of a CCP function, the M smoothness is equivalent to the coercive, okay? So by the coercive, we can see that first we expand this, okay? We expand this square term. We have the first x minus y square, and we have these terms here. Since f is smooth, then we know that the gradient of f is coercive. And since the gradient is coercive, this is greater than 0, okay? This terms is greater than 0. So we can get, so this term is less, okay? This negative, this whole terms with this minus 4 over L is negative. So we can get this is less than y minus x minus y, okay? So this inequality tells us this identity minus 2 over L grade f is a non-expensive operator, okay? This, you can regard this is tx minus ty, is less than x minus y. Okay, so since this part is this red part is non-expensive, then the convex combination is averaged, okay? So this operator is averaged, but with the assumptions that the alpha is less than is in this term, okay? So in this sense, since it is averaged, we use the theorem 1, which we discussed before, that this sequence, okay, this iteration converge, okay, this iteration converge. And let's go back to say the assumptions compared with the assumptions we used before. We just assume that f is L smooth, okay, but in the previous analysis about the convergence, we can go back. Yeah, here. In this slide, we analyze the convergence of gradient descent method, but with respect to the conjunction, okay? If we want this t, to this operator identity minus alpha grade of f to be a contraction, we do not need that L smooth. We also need the f to be strongly convex, okay? But with the theorem 1 here, if we use the definition of theta averaged, we can just assume here, we just assume f is L smooth without any strong convexity assumption, okay? And then we consider about the forward step method. The idea is the same, okay? The solution, we can get the solution by this fixed point iteration, and if f is beta co-coercive, then the whole operator, the identity minus alpha f, is averaged, okay? Is averaged if this f is beta co-coercive, okay? So of course you can use the definition of contraction to analyze this method, but you need to assume that beta f is strongly convex and the Lipschitz continuous, okay? It's a stronger assumption. Okay. The average iteration, the fixed point iteration with average operator, we call it cross no-cell scale-man iteration. Okay? If the lambda k equals lambda, which is a constant, then it is what we have discussed in the theorem 1. This one has been first studied by these two guys in 1953 and 1955. It's a tool. It's a kind of a theorem for the fixed point iteration, but it can also be used for analysis of convergence in optimization in the numerical linear algebra or the partial differential equations. So in one word, it is very useful. And this iteration, the result about this iteration has also been developed in the last last 10 decades or 20 decades. Okay, so we can give some extensions of this iteration. Okay, first is that instead of using lambda, we're using lambda k here. Okay, it means in each iteration, this convex combination can be not fixed. You can change it because sometimes we can imagine that in some cases, the operator t can accelerate the iteration. Sometimes the identity operators can accelerate the convergence. We can analyze an example here. Okay, it's still about the convex feasibility problem. It's set A and set B. We want to find a set X belongs to A and B. We want to find a point. Okay, we have analysis before. If you use the xk plus 1 equals to the composition of RB and RA, the composition of the reflections, this doesn't work, okay? This didn't work. So we use what? We can use xk, composition of two operators. Theta, we use theta k. Theta ki plus I minus theta k times identity 1 minus theta k, the reflection of B, composition of theta k identity plus 1 minus theta k reflection of A. This is the operator, okay, and the input is xk, okay. This extension of this extension means in some cases we can increase the theta k here if the identity can increase the convergence. If the reflections can accelerate the convergence. We decrease the theta k here. We can see example. If we use, this is x0, if we use the reflection, we get here. So if we use the combination, okay, if we use a combination of identity with reflection, we may get some point here, okay? We may get some point here, or maybe closer, okay? It gets closer at least to set C. So in these cases, because the interior of set B and the interior of set C is empty, so if you use a reflection, you see it go to another side. The distance didn't decrease. But if you make combination with identity, it will get closer. So in these cases, we can consider maybe we can increase the value of theta k. We mix the identity operator has more compact in the iteration, okay? And we have another two kind of generation of this Krasnoselski main iteration. The first is with perturbation, okay? We can have two perturbations here. And if the perturbation is summable, then we can still conclude that this iteration converge if T is non-expansive operator, okay? And another one is called the generalized Krasnoselski main iteration. Here, the residual is outside, okay? And we have beta k, alpha k, beta k here. The advantage of this iteration is that we do not assume that the sum of them is equals to 1, okay? So this can somehow generalize your algorithms. For example, in your convex combination, in convex optimization or variational inequality, okay? And but we need some assumptions like the sum of beta k times alpha k times beta k equals to infinity. The residual is summable, okay? And this about the 1 minus alpha k minus beta k. And also the T is non-expansive. I mean, this kind of generalization of fixed point iteration theorems can give you some new ideas to design the algorithms to solve the optimization problems, okay? Because here we have less restrictions on this parameter, okay? On this parameter alpha k, beta k than the original one we used in the theorem 1. Okay, so this is what I want to discuss in the first slide, okay? We discussed monotone inclusion problem, monotone operators, fixed point iterations, and non-expansive operators, okay? Next, we will give some reference, okay? The first reference is somehow a relatively new book about optimization. I used a lot of things from this book, and because it somehow has a similar perspective to analysis of the algorithms. I mean, with the abstraction of the monotone operators and the proximal point method. And also, second one is a book. It's the second edition of this book, Convex Analysis and Monotone Operators, okay? But the result there is in Hilbert space. But it has almost every result you want to use. This book is not good for, it's not very friendly for reading, but it's good for check the result whether you want, okay? And this is a very classic book in convex analysis by Rockefeller. Many very important results, and the theorem was first established in this book. Okay, so next we go to the the second slide, okay? In this slide, we will talk about first approximate point method, okay? In the first slide, we talk a lot of things, but it seems that we didn't propose or define the approximate point officially. But here we will define it officially, okay? And the resolvent is a definition which is related to the approximate point method. If you want to analyze the convergence of the approximate point method, you need to study the property of the resolvent, okay? After this, we will introduce the splitting method, okay? First, the splitting inclusion problem, then the splitting method. Okay, so we will talk about the resolvent and the approximate point method. Okay, so we recall what is a monotone inclusion problem. It's to find a point x such that 0 belongs to the ax, okay, where a is monotone. It is equivalent to say that we want to find x belongs to ax plus x and x belongs to a plus I x. Okay, so by the analysis here, if we want to first we have a fact that the solution of this problem is the fixed point of this operator. Okay, so if we can find the fixed point of a plus identity, we can find the solution of this inclusion problems. So we have two possibilities. We can use the operator a plus I here, or the inverse. But I use this equal in the red because sometimes the equal is not correct here. We need to use belongs to. I will explain it more later in the following slide. Okay. Let's go back to a very classical problem in the partial differential equation. Okay, the Cauchy problem. We have a Cauchy problems. Okay, we have an initial condition, and we want to, and the x minus x prime belongs to the axt. Okay, with the time step size alpha k. Sorry, there should be alpha k here, lambda k. There is a typo here. I apologize for that. This should be alpha k, and there is alpha k here, and this should be alpha k. Okay. But anyway, the idea is to solve these Cauchy problems. We have two kind of basic methods. First is the forward Euler method, okay, and the second is back Euler method. One is explicit method, another is implicit method. So what we should use here, but usually we see that backward Euler method has better properties, better performance, okay? And we can interpret the proximal point method from the point of view of the back Euler method, okay? I will analyze it in the blackboard. From the back Euler method, we have xk minus xk plus 1 over, okay, we use alpha k here, okay, belongs to the a, the input is a plus 1, okay. So this is equivalent to xk minus xk plus 1 belongs to alpha k a xk plus 1. So it is equivalent to xk belongs to xk plus 1 plus alpha k a xk plus 1. It is equivalent to xk belongs to identity plus alpha k a and xk plus 1. Okay, and we can write it equals to the xk equals 1 equals to identity plus alpha k operator A, but inverse xk. Okay, so this is the backward Euler method. Of course, if you can, if you have explicit form of the inverse, you can write it in this way. And this is also what we call the proximal point method looks like. Okay, so what is a proximal point method? The proximal point method is for solving maximal monotone or inclusion problems with this kind of with this kind of scheme. Okay, be careful. We use I minus alpha k inverse here. Let's go back to the analysis here. Here, we are by the equivalent statement here. We can think about two possibilities. First, use I plus identity. Another, use I plus identity inverse. Okay, but why did we choose the I plus alpha identity inverse, not the original one? We have two motivations. Okay, why not the forward Euler method? Okay, because here is equivalent to the backward Euler method, as I mentioned, as I analyzed there. First is, if A operator A here is maximum monotone operator, then the inverse of I plus alpha k is average operator, which we define as J alpha A, which we call this is the resolvent. Okay, this is a resolvent with respect to the operator A. Another is the the resolvent of A is single valued. Okay, so this is why we can use the equal here. Okay, another way, if you want to use this kind of iteration without the inverse, okay, you cannot use the equal here. At least you need to analysis. It's better to use belongs to, okay? Belongs to. Because if A is maximum monotone, you cannot guarantee the A plus identity is maximum monotone. But we can guarantee that the resolvent of A, which is the inverse of I plus I, the identity plus alpha A, it is single valued. So this is well defined. So this iteration is a well defined, and also we can say it converge because the theorem 1 we analyzed before. In theorem 1, we require the iteration, the operators in iteration is average operator, and fortunately here the resolvent G alpha A is averaged. Okay, this is the most beautiful things in the maximum monotone inclusion problems and the fixed point iteration. I rewrite it here. So we have a problem, inclusion problem. Okay, the operator here is maximal monotone. And we have algorithms here, xk plus 1, which is equals to I plus alpha A minus xk. We call it G alpha A. The resolvent, okay? If A here is maximum monotone, then this operator here is formally is 1 over 2 averaged. Okay? So, as long as you have a maximum monotone inclusion problems, you will have a corresponding iteration, which is called proximal point method, and the operator is resolvent, and it's 1/2 averaged. Okay, so we have a kind of corresponding between maximal monotone operator and I should say operator and 1/2 averaged operator. Okay, and how do we connect them each other? We use the maximal monotone operator and its resolvent. Okay, so this is why I think it is a very beautiful theorem. Okay, and of course the averaged operator guarantees a convergence. Okay, so before we study the convergence of the proximal point method, we need first to study the property of this JLA, which is a resolvent of operator A. Okay, so the resolvent of A is defined by the identity plus I inverse, and correspondingly, we can define the reflect resolvent A, which equals to the 2 times the resolvent of A minus identity. You just recall, you can regard it as the resolvent A is a projection. Okay, if this is projection, J is a projection, then A is a reflection. It's constant with the projection and the reflection, as we mentioned before. Okay, and it's also called Calais operators or reflection operator. Okay, but we assume that alpha is greater than 0. We always assume alpha or alpha k. No matter you use alpha or alpha k, but it's a positive number. Okay, next we will introduce a very important algorithms. Actually, the algorithms guarantee what I mentioned before, the relation between the maximal monotone operator and the average operator. But here we will say it more explicitly. Okay, so we assume that A is maximum, the resolvent is defined in this way, okay? The resolvent GA is defined in this way. First, we know that the domain of the GA is a range of the I plus identity. This holds automatically by the definition of the resolvent, okay? This is trivial. Second, GA is firmly non-expansive. Okay, sorry for using this here. You can also say firmly non-expansive is 1/2 average, okay? GA is firmly non-expansive or 1/2 average if and only if the operator A is monotone. Pay attention. We do not need to assume A is maximal monotone. If A is monotone, we already get the firmly non-expansive, okay? But why the maximal monotone is very important? Because if we have the A is maximal monotone, okay, and we can have a further result, we can see that the domain of the resolvent is a whole space. But why it is good? I mean, the domain is a whole space. Why is it good? Because if we do the proximal point iteration, proximal point method, if this operator has a full domain, it is much easier for us to analyze the convergence, okay? Because everywhere the operator is well defined everywhere, you can use the algorithm very conveniently. Okay. So, and the third one is called Minty surjective theory. Okay, the third one is also called Minty surjective theory. Here we give a picture to describe the the first part of the theorem's to give a geometric interpretation of the first conclusion of the last theorem. In this picture, from the left to right on each row, it's the graph of A, graph of identity plus A, and the graph of the resolvent, okay, the resolvent GA. It's a graph from a very recent paper by the Convergence, okay. So first we say this is a non-monotone operator, okay, and this is it's the A plus the identity. We can see that the range of this operator is just the domain of the inverse, okay. It's the same, and this one is monotone, but not a maximum monotone, and this one, the A is maximum monotone, okay, maximum monotone, and this is non-expansive. And we see that this in the last one, since this operator A is maximum monotone, and then this A plus I, the range of the A plus I is the whole space, and then the domain of the resolvent is the whole space, okay. And to prove the theorem 1, actually because of the time we cannot prove it today, but we will prove them, all of the result here. First we will prove the second one, okay, because the first one holds automatically, and then we'll prove the second one, and also we will prove the conclusion about the domain of the resolvent, which is which is a very famous Minty theory. To prove this result, the second one, which if A is monotone, then the resolvent is firmly monotone, we need to recall these conclusions. If T is firmly non-expansive, then which is equivalent to say T is 1 over 2 averaged, and which is also equivalent to say 2 times T minus identity is non-expansive. We can use this to prove that the resolvent of a monotone operator is averaged, but we will analyze this very carefully next class. We just want to mention a little bit about the Minty theory here. Okay. The Minty surjective theory says that the resolvent of a maximum monotone operator is a whole space. It is important and very useful result. Another thing is the proof of the Minty theory is also very interesting, because the ideas there is we define a representation function and use this function to represent the maximum monotone operator, and then we use the conclusions about the conclusions about the functions to first analyze this representation function, and then make the conclusion about this function, and eventually make a conclusion about the maximum monotone operators. So in the next class, we will introduce this representation function, which is called a Fitzpatrick function. If A is monotone operator, okay, then its Fitzpatrick function is CCP and satisfies these two inequalities. With this assumption, with this function, this representation function, we can prove that the range or the domain of resolvent of a maximum monotone operator is a whole space. We just take a very brief look at the proof. Here, you see, we use the property of the function capital FA, which is a representation function. Since this function is convex, so the we can use the subgradient inequality of response to this function, okay? So actually, the result about the monotone, maximal monotone operator comes from the property of its corresponding representation function. So this is another thing, very interesting thing about the Minty theory. This representation function established the relation between the maximal monotone operators and the convex functions. If you want to know more about this, you can on the YouTube. There is a presentation by the Professor Regina on the SEM in 2002. He introduced the theory about the representation function and the enlargement of the maximal monotone operator, and he established the relation between the monotone operator and the convex function. Okay, this is all what I want to talk about today. Tá bom, eu vou fechar agora.